Some log expressions can be evaluated quite simply in our head or with a little bit of work on paper, even though they may not seem entirely intuitive at first. Keep in mind that if we have an expression like the log base 7 of 1, what we're saying is that that has to be equal to some value y, which again means we can rewrite this in exponential notation as 7 to the y is equal to 1. That means we just need to find that value that we would raise 7 to in order to get 1, which in this case would be 0. So the log base 7 of 1 would be equal to 0. Similarly, in example 15, we would get 12 to the y is equal to 144. That would happen if y is equal to 2. So the log base 12 of 144 is equal to 2. We can apply that same approach to evaluate any logarithm that doesn't have variables contained within it, though sometimes it can be a little bit trickier. In example 16, we have the log base 1/2 of 32 has to be equal to some number. That tells us that 1/2 raised to some number is going to be equal to 32. In this case, we could determine that 2 to the 5th power would be equal to 32. But what we have as a base of 1/2, we could rewrite this as 1 over 2 to the negative 5th power, which would still be equal to 32. So that tells us that our value for y should be equal to negative 5. In example 17, we have the log base 8 of 8 to the 71st power. Since we have a log base 8 and an exponential base 8, those two automatically cancel each other out, leaving us with just 71. The other way to evaluate this would be to use properties of logarithms to bring that 71 out in front and rewrite this as the log base 8 of 8. And then it becomes a little bit clearer how when that becomes 1, we would end up with 71 times 1, or just 71. Example 18 would be very similar. Keep in mind if we have ln, that natural log statement, that's a log base e of e to the negative 1. That log base e and exponential base e would undo each other as inverse operations, leaving us with just negative 1. In example 19, we have 2 raised to the log base 2 of 7 power. Again, this isn't terribly intuitive, but if we keep in mind that idea that exponentials and logs are inverses of each other, as long as those bases are the same, those two functions will just undo each other, leaving us with 7. In example 20, we have the log base 15 of 3 plus the log base 15 of 5. There's no immediate trick to apply to this like we used in the previous examples. But if we use properties of logs, since we have that same base for each statement, we can combine this as the log base 15 of 3 times 5, or the log base 15 of 15. So if our base is equal to what we're taking the log of, that's going to give us a result of just 1. We can also rely on our calculator to evaluate more log problems for us than what we've seen so far, using something called the change of base formula. As long as a and b aren't equal to 1, and m is some positive real number, we can rewrite the log base a of m as the log base b of m, meaning we can change that log to any base we want, but then we also have to divide by the log base b of whatever that original base was. This is most useful for converting things into a log base 10. Because your calculator can evaluate things that are log base 10, or converting them into a natural log, because our calculator can also evaluate that for us. We want to apply that idea in examples 21 and 22. In example 21, we can convert this into a log base 10 by taking the log of 42 divided by the log of 7, which was the original base. Or if we wanted to use natural logs, we could convert it into the natural log of 42 divided by the natural log of 7. In either case, regardless of which approach we use, we should get a result of approximately 1.921. In example 22, we can apply the same approach. We'll take the log of 4 over the log of the original base, which in this case was 1/5. Or again, we can take the natural log of 4 over the natural log of 1/5. Regardless of which new base we use, we get approximately negative 0.861. As a side note for this problem, a handy trick that we can use to rewrite this second expression would be to recognize that this is the same thing as the natural log of 5 to the negative first power. If we bring that exponent down as a factor in front, this is the same thing as the opposite of the natural log of 5, meaning this expression that we had could be written a little bit more simply as the opposite of the natural log of 4 over the natural log of 5. That can come in handy for some equation solving, which we'll do later on, or simply rewriting a given problem in a simpler form. Isn't really necessary right now, but it's a good idea to be aware.